Section 1 Introduction. 1 Introduction. The rapidly advancing field of large language models, LLMs, is poised to significantly change our understanding of human language processing and propel the progress of artificial intelligence, AI. OpenAI's ChatGPT, for instance, has already served over 100 million active users within just 3 months of its launch, making it the fastest growing application to date. But the influence of LLMs extends beyond chatbots. They are increasingly becoming a part of our digital lives, with key service providers incorporating these powerful models into copilot programs and search engines, thereby altering the way we interact with the digital world. LLMs are some of the largest and most computationally demanding deep neural networks, DNNs. The latest GPT-4 model, for example, is believed to have trillions of parameters and could take months to train. Over time, researchers have tried to improve the performance of distributed DNN training and inference by optimizing parallelization strategies, implementing sophisticated scheduling, advanced compression, and even altering the network topology itself. However, despite these efforts, LLMs still require a substantial amount of raw computing power. The GPT-3 model from 2020, for instance, already requires 355 GPU years on NVIDIA's V100 GPS. As the pace of Moore's law slows down, the growth rate of LLM size and computation requirement is outpacing the advancement of accelerators, making the use of large-scale GPU clusters inevitable. Our discussions with leading machine learning architects in the industry suggest that the next-generation LLMs will likely require over 30,000 GPUs of computing power to complete training within a reasonable timeframe. A GPU-centric cluster typically uses 2 types of connections. The first type involves a few GPUs, for example, 8 for a DGX-H100 server, located within a high-bandwidth domain, or HB domain, through a short-range communication protocol like NVLink. The second type of connection forms a network capable of any-to-any GPU communication using RDMA-capable NICs, connected in a variant of the CLO network. This cluster uses the RDMA protocol on this network to bypass CPU and OS entirely through GPU direct. However, scaling up RDMA networks to tens of thousands of GPUs presents challenges. Previous research has shown that large-scale RDMA networks are susceptible to deadlocking and PFC storms, which can degrade performance. Moreover, as the scale increases, CLO architectures become prohibitively expensive. Data center providers often resort to oversubscription to manage the cost of the cluster, which exacerbates the deadlocking issues. Previous research has proposed several techniques to enable large-scale RDMA networks and reduce their cost. These methods fundamentally rely on the assumption that the network is capable of any-to-any communication. This assumption has been the foundation upon which data centers have been conceptualized and developed for several decades. In this paper, we question this assumption and demonstrate that LLM training traffic does not require any-to-any connectivity across all GPUs in the network. We argue that with the optimal parallelization strategy, an LLM training workload requires high-bandwidth any-to-any connectivity only within small subsets of GPUs, and each subset fits within an HB domain. Communication across the HB domains only occurs for a few GPU pairs, and the traffic volume is minimal. Therefore, the traditional any-to-any approach for building data center interconnect adds unnecessary complexity and cost for distributed LLM training. We propose a network architecture that accurately reflects LLM communication requirements. In this architecture, a cluster is first divided into multiple HB domains, each interconnected with a full bisection bandwidth any-to-any interconnect. Across the HB domains, instead of forming a CLO to support any-to-any communication, the network only connects sets of GPUs with network traffic. We show that our LLM-centric network architecture achieves the same performance as a full bisection bandwidth any-to-any CLO cluster while reducing the cost by 37% to 75%. Section Summary. The introduction highlights the growing importance of large language models, LLMs, in revolutionizing language processing and AI. LLMs like OpenAI's ChatGPT are being integrated into various applications, but their large size and computational requirements necessitate hyperscale GPU clusters. The paper challenges the assumption that LLM training requires any-to-any connectivity across all GPUs in the network and proposes a network architecture that partitions the cluster into high-bandwidth domains, reducing complexity and cost while maintaining performance. Section 2 Motivation. In this section, we'll first explain the structure of a traditional GPU-focused cluster. Then, we'll delve into a detailed analysis of LLM traffic patterns to justify a network architecture that differs from the traditional design. Let's start with the current design of GPU clusters. Traditional networked clusters are built to handle CPU-intensive tasks using a multi-layer CLO network, as shown in the figure. This structure, known as a fat tree network, has been extensively researched in the system and networking fields. In a typical fat tree-based cluster, each server has one network interface card, NIC, with a speed ranging from 40 gigabits per second to 400 gigabits per second. A group of servers, denoted as K, are organized into racks that connect to top-of-the-rack, TOR, switches. These TOR switches then connect to aggregation switches to provide connectivity across racks, forming a pod. Finally, these pods are interconnected with spine switches, enabling communication between any servers in a CPU cluster. However, the increasing demand for network-intensive machine learning tasks has led to the prevalence of GPU-centric clusters, where each GPU has its own dedicated NIC. The figure shows the network architecture of a typical GPU cluster. Each GPU has two different communication interfaces. I, an NVLink interface for high bandwidth but short-range connections, and E, a conventional RDMA-enabled NIC. The NVLinks connect K GPUs, providing terabits of non-blocking bandwidth in-out per GPU. For example, 7.68 terabits per second for 4th-gen NVLink. This group of GPUs with fast interconnect forms a high-bandwidth domain, HB domain. Traditionally, HB domains were limited to a single server, like DGX servers with K equals 8 or 16 GPUs. However, NVIDIA recently announced the GH200 supercomputer that connects K equals 256 Grace Hopper superchips to form one HB domain across multiple racks. However, some LLMs take too long for a single HB domain to train, even with 256 GPUs. For example, the Palm 540B model would take 117 days to finish on a GH200 supercomputer, assuming perfect GPU utilization. These models require parallelization across multiple HB domains. To train an LLM across multiple HB domains, GPU cluster operators use RDMA-capable NICs to connect multiple HB domains together. The traditional network architecture to connect HB domains is known as a rail-optimized network. In a rail-optimized architecture, GPUs within an HB domain are numbered from 1 to K. A rail is the group of GPUs with the same index, or rank, on different HB domains, interconnected with a rail switch. For example, the figure shows Rail 1 and Rail K in red and yellow color, respectively. These rail switches are then connected to spine switches to form a full bisection any-to-any CLO network topology. This network ensures any pair of GPUs in different HB domains can communicate at the network line rate, 400 gigabits per second InfiniBand network for GH200. For example, traffic between GPU 1, domain 1 and GPU 1, domain 2 goes through rail switch 1 only, while traffic between GPU 1, domain 1 and GPU 2, domain 2 goes through the respective rails and the spine switches. Section Summary. In this section, the authors discuss the motivation behind the design of a network architecture for GPU-centric clusters. They compare the conventional design, which is focused on CPU-heavy workloads, with the rise of network-heavy ML workloads that require parallelization across multiple high-bandwidth, HB, domains. To enable training large language models, LLMs, across multiple HB domains, cluster operators use RDMA-capable NICs to interconnect them in a rail-optimized network architecture, ensuring efficient communication between GPUs in different domains. Section 2.2 Analyzing network traffic of LLMs. We're going to delve into the traffic patterns and processing times of three advanced language models: OpenAI's GPT-3, Meta's OP3 to 175B, and Google's Palm 540B. These models are run on a network of hundreds of NVIDIA GH200 supercomputers. Each of these supercomputers has a two-tier NV switch architecture, which allows for a high-speed data transfer rate of 2 petabits per second across 256 H100 GPS. Each GPU also has a Connect X7 HCA InfiniBand network interface, which provides a network bandwidth of 400 gigabits per second for each GPU. In this setup, each GH200 supercomputer forms a high-bandwidth, HB, domain. We use a benchmarking strategy from NVIDIA to ensure the GPUs are used optimally. We use a combination of data parallelism and intra-operator model parallelism, but our findings would be similar if we used pipeline parallelism. The data parallelism synchronization uses a hierarchical all-reduce algorithm to limit traffic across HB domains. We use the best parallelization strategy for each language model and calculate the resulting traffic pattern. It's important to note that for the Palm model, the batch size changes throughout the training. We've included figures that show the traffic type distribution of one training iteration across server pairs for a cluster of 128 GH200 supercomputers, and the percentage of volume for each type of traffic. There are two main types of communication: intra-operator model parallelism traffic and all reduced traffic generated by data parallelism. The model parallelism traffic occurs within GPUs that are part of a model parallel group, which always fits in an HB domain. For data parallelism, the hierarchical all-reduce algorithm divides the communication into two stages. The first stage synchronizes parameters across HB domains, while the second stage is within them. The algorithm ensures the second stage carries more traffic to better utilize the available bandwidth. While these types of traffic do not overlap between different pairs of GPUs, our figures show that over 99% of GPU pairs carry no traffic and less than 0.25% of GPU pairs carry model parallelism and second-stage data parallelism traffic between them. At the same time, these traffic types account for over 90% of the total transmitted data. These two types of traffic stay within HB domains, suggesting efficient usage of HB domain bandwidth and low demand on the network fabric interconnecting HB domains. This pattern is consistent across all models, indicating that building a cluster with any-to-any connectivity on top of HB domains for language models is excessive. Within HB domains, the interconnect needs to support heavy any-to-any communication for training a diverse set of language models. To illustrate this, we've included heat maps of the traffic matrices during a training iteration for GPT-3 and OP3 to 175B. In this plot, every consecutive set of 256 GPUs resides within the same HB domain. The figures demonstrate the communication pattern within an HB domain. The traffic volume is significant, up to 1 GB across server pairs, and the pattern varies due to different parallelization strategies across these models. The squares on the diagonal represent the model parallelism traffic, while the rest of the off-diagonal lines represent the second-stage data parallelism traffic. An any-to-any interconnect within an HB domain provides the maximum flexibility to accommodate different language models. However, the high bandwidth any-to-any connectivity required within HB domains is not needed across them. Our figures zoom out to the first 4 HB domains, where the first-stage data parallelism traffic across HB domains occurs. Compared to the traffic within an HB domain, the cross-HB traffic is much smaller, approximately 1 MB per entry, and more sparse. This is because cross-HB domain communication only occurs between GPUs with the same rank. Furthermore, the pattern is homogeneous, as the cross-HB domain communication pattern remains the same across language models. These observations suggest that it is possible to remove links that do not carry any network traffic without hurting the training performance of language models. Our analysis shows that 33% of the links in an any-to-any 400 gigabits per second CLO network are removable. We've included a figure that illustrates the training iteration times for this alternative network, labeled as any-to-any trimmed 400 gigabits per second, compared to the state-of-the-art. Given that the disconnected links do not support any traffic, these two topologies deliver identical performances. To put this into perspective, we also consider an ideal performance by assuming all GPUs in the cluster are interconnected with NV-switch, forming a monolithic 7.68 terabits per second full bisection bandwidth any-to-any network, which represents a 19.2 times increase in the full bisection bandwidth compared to the state-of-the-art. Such a network is impossible to build in practice. The performance improvement, however, is not proportional to the added bandwidth, ranging from 1.06 times to 1.88 times for all models. Such a result provides compelling arguments for language model cluster operators to reassess the conventional any-to-any network design. Section Summary. The section analyzes the traffic pattern and iteration time of OpenAI's GPT-3, Meta's OP3 to 175B, and Google's Palm 540B language models in a cluster of NVIDIA GH200 supercomputers. The analysis reveals that the majority of communication occurs within the HB domains, with intra-operator model parallelism, MP, traffic and all reduced traffic generated by data parallelism being the primary types. The study suggests that it is possible to remove links that do not carry any network traffic without affecting the training performance of the language models, indicating a need to reassess the conventional any-to-any network design for LLM clusters. Section 3. Our proposed LLM cluster. In this section, we're introducing a new network design specifically tailored for LLM clusters. We've developed a mathematical model to help determine the parameters for these clusters, and we're providing a comprehensive set of guidelines to assist in this process. We're proposing a unique network architecture that deviates from the standard any-to-any communication across all GPUs. We've named this architecture rail-only. In contrast to a traditional rail-optimized GPU cluster, our network maintains the HB domains and only allows connectivity across the same rail. To implement our proposed architecture, we suggest removing the spine switches and repurposing all the uplinks connecting rail switches to the spine as downlinks to GPUs. This means that each rail is connected by a dedicated but separate CLO network. We base our analysis on this realization of the rail-only network, but other technologies could also be suitable for other rail interconnections. Our rail-only network architecture eliminates network connectivity across GPUs with different ranks in different rails. However, communication is still possible by forwarding the data through HB domains. For example, a message from GPU 1, domain 1 to GPU 2, domain 2 can be first routed through the first HB domain to GPU 2, domain 1 and then transmitted to the final destination through the network. While our analysis shows that LLM traffic doesn't require such forwarding, this connectivity might be needed for control messages, measurement, or training other DNN models in this cluster. We'll discuss handling other DNN models later in the paper. We've also conducted an analysis of our rail-only network. We've considered a network with n GPUs and an HB domain of size k. The bandwidth for each HB domain is represented as B_F and the network bandwidth as B_S. We've focused on using hybrid two-stage data and model parallelism as the parallelization strategy and derived a mathematical model for the training iteration time and optimal model parallel group size. The total time required for a single iteration is the sum of computation and communication times. We've modeled the computational duration of the model as the ratio of the required amount of floating point operations to the aggregate flops of the cluster. For the collective communication durations, we've calculated the bandwidth time only since the latency term is constant for our choice of collective communication algorithm and small relative to the bandwidth term. For all three types of communication, we've based our calculations on bandwidth and latency optimal collective communication algorithms implemented with all-to-all communication within connected sets of GPUs. Using this formula, we can calculate the optimal n_m, which is the optimal model parallel group size. Interestingly, n_m is independent of k, b_f, and b_s, indicating no dependency on the size of the HB domain or the exact bandwidth of any interconnect. Section Summary. In this section, the authors propose a new network design called the rail-only network for LLM clusters. They provide guidelines for determining the parameters of such clusters and explain how communication between GPUs with different ranks and different rails can still be achieved through HB domains. The authors also present a mathematical model for analyzing the network and derive an optimal model parallel group size for training iterations. Section 3.3 What is the ideal size of an HB domain? 3.3 Determining the optimal size for an HB domain. The next logical question in our design process is, what is the optimal size for an HB domain? To answer this, we experimented with different HB domain sizes, k, and measured the training iteration time for two models, GPT-3 and OP3 to 175B, using GPU clusters of varying sizes, 16,384, 32,768, and 65,536 GPUs. For each cluster size, we use the optimal n_m, value, which we derived from the bandwidth and computational ability parameters of the GH200 supercomputer. We also calculated the training iteration time for the any to any 7.68 terabits per second scenario, which we consider as the ideal case performance. This scenario assumes a perfect situation where every GPU is connected with a full bisection NVLink fabric, or in other words, where k equals n. However, this scenario is not achievable in real-world conditions. In this ideal case, we use a non-hierarchical all-reduce algorithm to take full advantage of the uniform high-bandwidth interconnect. The iteration time in this case can be calculated as follows. The total number of floating point operations, m_flop, divided by the product of the number of GPUs, n, and the computational ability, c, plus the latency, l, divided by the product of the full bisection bandwidth, b_f, and the number of GPUs, n, multiplied by twice the tensor size, s_t, times the difference between the number of GPUs, n, and the optimal n_m, plus the product of the model's communication complexity, m_cc, the model's depth, the _chata, the difference between the optimal n_m, and 1. As shown in our results, the performance improvement decreases as the HB domain size increases. For instance, increasing the HB domain size from 32 to 64 results in a 12% and 37% reduction in training iteration times for GPT-3 and OP3 to 175B, respectively. However, A further increase from 512 to 1024 only yields a gain of 0.95% and 7.5%. This diminishing return in communication time gain can be explained by Amdahl's law, given that the computation time of the deep neural network, DNN, remains constant across all instances. We believe that the current GH200 supercomputer, with an HB domain size of 256, is well suited for large language model, LLM, training today, as long as an appropriate batch size is selected. We will discuss the analysis of batch size in a later section. Furthermore, future technological advancements that increase this size will further improve training performance, bringing the training iteration time closer to the ideal case, without the need for any-to-any connectivity in the network across HB domains. Section summary. The ideal size of the HB domain is determined by varying the HB domain size, K, and measuring the training iteration time for different GPU cluster sizes. The performance gain decreases as the HB domain size increases, with a transition from 32 to 64 resulting in a 12% and 37% reduction in training iteration times for GPT-3 and OP3 to 175B, respectively. The current GH200 supercomputer with an HB domain size of 256 is well suited for LLM training, but future technological advancements can further improve training performance without requiring any-to-any connectivity. Section 3.4 Impact of batch size on network design. We're going to discuss the influence of batch size on network design and then move on to an analysis of network costs. Firstly, let's talk about batch size. Our findings suggest that as the batch size increases, the optimal size for model parallel groups decreases. This allows for more data parallel communications to fit within the HB domain, which in turn improves overall performance. To illustrate this, let's compare two models, GPT-3 and OP3 to 175B. These models have almost identical structures, but the difference in their training iteration time comes from their batch sizes. GPT-3 uses a batch size of 32 million tokens, while OP3 to 175B uses a batch size of 2 million tokens. We further explored the effect of batch size on training time by testing a PaLM 540B model on a cluster of 32,768 GPUs. We varied the HB domain size from 256 to 1024. During training, the model automatically adjusted its batch size from 512 to 2048 sequences, which is equivalent to 1 million to 4 million tokens. We found that the iteration time followed the same pattern for all HB domain sizes. However, due to Amdahl's law, the relative performance improved as the batch size increased. For instance, when the HB domain size was 256, the relative performance increased from 53% to 74% as the batch size increased from 512 to 2048 sequences. Previous studies have shown that large language model, LLM, training benefits from larger batch sizes, which makes it a great match for our rail-only design. Moreover, while batch size is typically a machine learning-centric metric for optimization, our analysis shows that its impact on overall training performance extends beyond the total number of iterations needed for convergence. Now, let's move on to network cost analysis. Our rail-only network architecture smartly reduces the network resources needed for LLM training by eliminating unnecessary network connections. We compared the network cost of our approach with that of the most advanced rail-optimized GPU clusters. We calculated the number of switches and transceivers needed for each network design and estimated the total network equipment cost based on previously reported figures, 374 per transceiver and 748 per switch port for 400 gigabits per second. We focused on using only electrical packet switches to build the network, but using optical direct connect technology could further reduce costs. We'll discuss direct connect networks in a later section. We listed the number of switches and transceivers needed to build both the current network architecture and our proposed architecture in a table, taking into account different cluster sizes and network switch radix. For the current architecture, to use the least amount of network resources, each rail of GPUs is not physically separated in some cases. Therefore, the data center operator must manually configure the switch to achieve the desired isolation across rails to achieve the rail-optimized design. Our rail-only design significantly reduces the network cost by 37% to 75% compared to the current design while maintaining the same performance. This reduction comes from eliminating core layer switches and reducing the number of switch tiers within each rail. Interestingly, switches with a radix of 64 provide the smallest cost reduction in both cluster sizes. In this case, the current design requires a 3-tier CLO network, while the rail-only design requires 2 tiers for each rail. However, our design only requires 3/4 of the total number of switches while still achieving the same performance as the current design. Section Summary. The impact of batch size on network design is analyzed, showing that as batch size increases, the optimal model parallel group size decreases, leading to improved performance. The study also compares the network cost of a rail-only architecture with state-of-the-art rail-optimized GPU clusters, demonstrating that the rail-only design reduces network cost by 37% to 75% while achieving equivalent performance by eliminating core layer switches and decreasing the number of switch tiers within each rail. Section 5 Discussion. In this section, we'll discuss various aspects of large language models, LLMs, including their growth trends, inference, network topology, other machine learning workloads, and fault tolerance. Firstly, let's talk about the LLM trend. The computational needs of LLMs are growing at a faster pace than the advancements in AI accelerators and network speed, especially as Moore's law is slowing down. This situation calls for the use of large-scale clusters and more efficient interconnections. Our proposal to eliminate any-to-any network connectivity is a step towards meeting the network requirements for LLM training and supporting the growth trend of LLMs. We also recognize ongoing efforts to decrease the size and resource needs of language models without sacrificing performance. Our design, which reduces network resources and maintains performance, complements these efforts and is beneficial even for smaller language models and clusters. Next, we'll discuss LLM inference. While this paper primarily focuses on the training workload of LLMs, inference is another crucial part of the LLM product cycle. Inference requires fewer computational resources than training as it involves moving less data through the LLM and only computes the forward pass. Therefore, each HB domain naturally becomes an inference serving domain, and the rail-only connections assist in balancing the load across multiple inference domains. A more detailed investigation of LLM inference is a topic for future research. Now, let's talk about the direct connect network topology. Data center operators can use direct connect network topologies for interconnection across the rails. To maximize the effectiveness of such designs, we suggest increasing the number of network interfaces connecting to each GPU through NIC interface splitting. We also recommend using reconfigurable optical switches for more flexible interconnections across HB domains. This design also allows for reconfiguring some connections across rails for upcoming workloads that behave differently from LLMs. We believe that combining our proposed design with optical reconfigurable network switches opens a new research area in IML clusters. Regarding other ML workloads and limitations, our proposed rail-only architecture, while specifically designed for LLMs, is efficient for many other DNN workloads when combined with other efforts. Recent works aim to make the parallelization strategy and collective communication algorithms bandwidth-aware for any DNN model, which already produce traffic patterns similar to those of LLMs. For parallelization strategies that require a small amount of traffic for GPUs across the rails, the cluster can use the forwarding described earlier. The main challenge of our design is the all-to-all communication across all GPUs, a common issue in recommendation models with large embedding tables. This forwarding scheme can cause congestion and degrade the performance of all-to-all traffic. We recognize that all-to-all traffic is one of the most challenging traffic patterns in ML workloads. Some potential solutions include reintroducing small any-to-any capacity through an oversubscribed network, using a fast reconfigurable network fabric, and reducing the amount of all-to-all traffic initially generated by adjusting the ML model itself. Finally, let's discuss fault tolerance. At first glance, the rail-only design might seem less fault-tolerant than a standard CLO network. However, if a rail switch fails in either network, all the GPUs connected to the failed switch will become unavailable, making the two topologies identical in terms of fault tolerance on rail switches. On the other hand, our design requires fewer switches, which naturally reduces the points of failure. Data center operators can add redundant capacity by including extra rail switches, and our design remains more cost-effective compared to the state-of-the-art any-to-any network design. Fault tolerance can also be increased with a direct connect network, as even if the control plane fails, an optical switch is likely to remain functional. Section Summary. The current growth rate of large language models, LLMs, exceeds the advancements in AI accelerators and network speed, necessitating hyperscale clusters and more efficient interconnects. Our proposed design removes any-to-any network connectivity, reducing network resources and maintaining performance even for smaller language models and clusters. Additionally, we suggest using reconfigurable optical switches and increasing the number of network interfaces connecting to each GPU to maximize the effectiveness of direct connect network topologies.